Hey, ladies and gentlemen, once again, I'm Erisa coming to take you through some online lessons. Today, we're going to talk about mutually exclusive events and independent events. We are starting our discussion with mutually exclusive events. Remember, last time, the previous lesson is about probability. We have been talking about two events of the same experiment. We talked about the probability rule for combining two events of the same experiment, and also talked about the other useful results. So today we want to talk about two events of the same experiment that cannot occur at the same time. Let's see. Let's consider events A and B of the same experiment. A and B are said to be mutually exclusive events if they cannot occur at the same time. Okay, we are saying that mutually exclusive events are those events of the same experiment that cannot occur at the same time. Okay, you perform an experiment and the events you are expecting cannot occur at the same time. For example, if there is a soccer game, if your experiment you are performing to look at the win of a soccer game, you can't have both teams winning. No, that will never happen. It will never happen. Okay, it is either a win, okay, or a draw, but not both teams winning. So team A winning and team B winning uh, cannot occur at the same time. You can't have A winning and B winning at the same time. It is either A or B, but not both A and B. So such events are called the mutually exclusive events. Okay. The same happens when we throw a die. You can't have, you can't score a 2 and score a 5 at the same time. It will never happen. It is always one face turning up. So the score of 3 and 5 are mutually exclusive. They can't occur at the same time. We can't have the two intersecting. So such events are said to be mutually exclusive events. So we are saying that mutually exclusive events can't occur at the same time. Okay. So what doing about it? The intersection? Let's write something about this. If A and B are mutually exclusive, then, okay, this is the most important thing about mutually exclusive events. Okay, then probability of A intersection B is equal to 0. Okay, since, okay, A and B, okay, are impossible events. Impossible events. You can't have both A and B occurring at the same time. So A and B is an impossible event. Okay, it is in fact supposed to be one. A and B is an impossible event. It cannot occur. Okay, for mutually exclusive, you can't have A and B. The most important point about mutually exclusive events is the intersection is gonna be 0. That's what you need only about mutually exclusive. And as a student, you have to understand which events can be mutually exclusive. For example, if they say the baby born is both a girl and a boy. That cannot happen, in normal, nature, you either have a boy or a girl, but not both. Okay. Yeah, if it ever happens, then I don't know how to treat it, but we are looking at a situation where you're getting only a girl or a boy. So you can't have a girl and a boy happening at the same time. So that's what we have to know about mutually exclusive events. So something you have to know if you want to present this in Venn diagrams is there is no overlap of A and B. It will never happen because they're not intersecting. There is no overlap of A and B. Okay. If you look at this as a sample space S, then you have event A and event B in the sample space, but they can't overlap. So that situation is what we call a mutually exclusive situation. Okay. And there is something we learned last time about the probability rule for combined events. Let me remind you. Okay. Remember, probability of A union B was equal to probability of A plus probability of B minus probability of the intersection. And we are saying that for mutually exclusive events, but for mutually, okay, exclusive events, okay, the probability of A intersection B is equal to 0. So what do we have? Probability of A union B will be just probability of A plus probability of B. This only happens for mutually exclusive events. Okay. And this is what we call, this is the combined rule. Okay. The rule for, let me change it. This is the rule for combined events. Combined mutually exclusive events. Okay. It is sometimes, if you want, you can call this the O rule. So that is what you need about mutually exclusive events. So it's all about intersection. The two events cannot intersect, therefore the intersection is 0. And if you want to go to the rule for combined events, then to reduce to probability of A union B equals probability of A plus probability of B. So next we look at an examples to emphasize the point. But one thing you have to know about mutually exclusive events, they are events of the same experiment. Okay. And they cannot intersect. That is it. All right, let's look at this example. Okay. It is still a printed example, but because the print is so small on my screen, when you watch, you'll not see it so well. So I've decided to rewrite it. Okay. So it is known that the probability of X equals to a half and probability of Y equals to a quarter. Given that X and Y are mutually exclusive events, first they want us to find probability of X union Y. So in the solution, What do we need? Okay, we are talking about the probability of X union Y. We know that the probability of X union Y is simply probability of X plus probability of Y for mutually exclusive events. And if you get probability of X, which is a half, and add to the probability of Y, which is a quarter, then you end up with 3/4. Okay, so the probability of X union Y is 3 out of 4. Next, they want, this is A. B, probability of Y intersection X. Remember, probability of Y intersection X, the same thing as probability of X intersection Y. And we know about something about mutual exclusive events, that the intersection is equal to 0. Don't even waste time calculating. Okay, C, the probability of Y intersection X complement. Okay, this is the probability of X Y intersection X complement is Y only. So this is the probability of Y minus the probability of Y intersection X. Okay, let me remind you about intersecting events so you can see what I'm talking about. If this is X and this is Y, okay, and they are intersecting, then this is Y intersection X, okay, complement. And this is this part is X intersecting Y. Now, these events are not intersecting the mutually exclusive events. Therefore, if you are looking at probability of Y and take out the intersection to have Y only, then the intersection is 0, and therefore for mutually exclusive events, this is the same as probability of Y, okay? And this is going to be a quarter. You are done. So this is a very simple question I've chosen for you. Let's see another example. Let's look at the second example. There are 10 red, 5 blue, 3 green, and 2 yellow marbles in a jar. John picks a marble without looking. What's the probability John picks a green or a yellow marble? Okay, so let's look at this question. It is a very simple question. This box has 4 colors. And the colors of our interest are green or yellow. So we shall use G to stand for green marble. Green marble. And we shall use Y to stand for yellow marble. Now, the probability of picking green will be simply number of green over number of the sample space. And the green marbles, when you check, they are 3 out of 10 plus 5, that's 15, plus 3, 18, plus 2, 20. Okay. Then probability of yellow, there are 2 out of 20. So probability of green or yellow, or means union, okay, or yellow. Remember the old rule for mutual exclusive events is simply probability of green plus probability of yellow. Okay, and this is 3 over 20 plus 2 out of 20, which is 5 over 20. In the lowest terms, this will be 1 out of 4. So the probability of green or yellow is 1 out of 4. And we are done. So next we talk about conditional probability. So in probability theory, conditional probability is a measure of the probability of an event occurring given that another event has occurred. Okay, yeah, the occurrence of the first event affects the occurrence of or event of interest. Okay, for example, if there are 10 people contesting or going for a beauty contest, and the 10th person is eliminated, okay, it somehow affects the chance of the first person winning the contest, okay, and in this case it increases because the occurrence of one event influences another event. So such a situation is what we call a conditional probability situation. Okay, more information. So if the event of interest is A and the event B is known or assumed to have occurred, the conditional probability of A given B or the probability of A under the condition B is usually written as, okay, so there are basically two main ways of writing this, okay. There is this probability of A given B, and this will be so common. You can use any. This is not so common, but for purposes of information, I've given it to you. So it is given probability of A slash B. Okay, this is probability of A slash B. Okay, or probability of A, then a bar, then B. But this is very common. Most people use this when they are writing. It is okay. That's how we write conditional probability. Probability of A given B. B has already occurred. Okay, what is the chance that A occurs? Are you understanding? Let's see. Let's look at a real life example to amplify the understanding of conditional probability. Okay, why the occurrence of some event can affect the occurrence of another event. Let's see this example. So this is a real life example. Normally, a person will always cough, and the chance that you have a cough when you are normal could be maybe 5%. But if you are sick, then you are most likely to be coughing. So we may write that the probability of cough, given that one is sick, okay, is 0.75. Now, this is something I've just written, but it is to emphasize the point that the sickness is increasing the coughing. Okay, so this is conditional. You are coughing a lot just because you are sick. But if you are to be normal, then the chances of coughing will be about 5%. Okay, so sickness increases coughing, and therefore this is conditional in this case. So if you have somebody contesting for area member of parliament, and the person has been a member of parliament for the last 4 terms, what is the chance that is going to win the incoming contest? So that is conditional. Given that the person has been winning, okay, does it increase his chances of winning? Okay, so that's what we call conditional probability. Now, how do we define conditional probability? The probability that A given B is equal to probability of A intersection B over probability of B. Okay, the occurrence of B affects A and reduces the sample space to B. Okay, this is how it is developed. Probability of A given B is number of A intersection B over number of B. The sample space reduces to B, okay? It no longer is because B dictates A, okay? And if we decide to divide through by number of S up and down, then it brings us to this result, and that result is so important. Some people prefer to write this as probability of A intersection B is the probability of A given B times the probability of B. Okay? Yeah, that is okay. It is the same result, but just cross multiplied. And You'll find this so frequently used. So, ladies and gentlemen, in my next discussion, I'm going to bring examples about conditional probability and we discuss them. Right now, let's stop here and call it a lesson. Okay, remember to subscribe and share this information with a friend. It is so important.